So this is Mr. P coming to you once again. Today is we're going to look at a special segment on the speed of sound, and this would be your e-learning lesson for Thursday, April 16th. Okay, so we had visited this topic once before in our last segment of e-learning. We talked about the speed of sound, how it is different in different materials. Okay, remember how it's fastest in solids, a little slower in liquids, and the slowest in gases. And we said it's about 343 meters per second, about like 760 miles per hour in room temperature air, which is at 20 degrees Celsius. Now, what we're going to talk about, one of the things we're going to talk about is how the temperature of the air affects how fast sound travels through the air. But again, just a few general things about sound first. So the speed of sound, again, is depending on the medium or the material it's traveling through. And fastest, again, it travels fastest in solids, Yes, fastest in solids and slowest in gases. Okay, so again, speed of sound depends on the medium through which it travels, mediums being solids, liquids, and gases. It travels fastest in solids and slowest in gases. So we're going to focus specifically on the speed of sound in air for the moment. So the speed of sound in air depends on the temperature of the air. So at 0 degrees Celsius, this would be at 32 degrees Fahrenheit, so the freezing point of water, basically. The speed of sound in the air is 331 meters per second. For every degree above 0 Celsius, the speed of sound is going to increase by 0.6 meters per second. For every degree below 0 degrees Celsius, the speed decreases by 0.6 meters per second. So our formula, V sound, so this means velocity of sound or speed of sound, is 331 plus 0.6 times the temperature. So basically a shorter version of that, 331 plus 0.6 times the temperature in Celsius. Okay, so the temperature has to be in degrees Celsius. So 331 plus 0.6 times T, which is the temperature in Celsius. So let's move this up and look at an example. All right, so again, our formula is 331 plus 0.6 times T, right? 331 plus 0.6 times the temperature in Celsius. So what is the speed of sound at 35 degrees Celsius? What is 35 degrees Celsius? That's the temperature, right? That's our T. So what we do is we'd say 331 plus 0.6 times 35. And of course, we go back to our order of operations in math where we want to do the multiplication first. So 0.6 times 35 ends up being 21. So I do 331 plus 21. And then finally I would get 352 meters per second. So, and it's what we would expect, okay, because the temperature, okay, at 35 degrees Celsius, okay, that is above 0. We said it starts at 331, and as we get further and further above 0 Celsius, our speed of sound should increase, and we got our expected result. So at 35 degrees Celsius, our speed is 352 meters per second. Remember, at 0 it was 331, so we saw an increase like we expected. And so all we do is plug in the temperature for T, do the multiplication first, then add 331 plus what you get when you multiply the two numbers. And so let's go ahead and look at couple relationships here. So remember we had the relationship that the speed of a wave in general was equal to the frequency times the wavelength, right? F was frequency. So this is for any wave, the speed of any wave, and lambda, that Greek letter, that was the wavelength. And we know that in general, okay, speed is equal to, or velocity is equal to distance over time. And if we rearrange the equations, we can get different forms like frequency equals velocity over wavelength. Again, think of dividing both sides of this equation by lambda, or the wavelength. And if we wanted the wavelength, then it would be velocity divided by frequency. Again, divide both sides by f. So if we look at velocity equals distance over time, again, we can always rearrange that. So distance would be velocity times time, or VT. We just think of cross multiplying. Time, okay, that would end up being distance divided by velocity. All right, so key equations here: velocity, or speed of a wave, equals the frequency times the wavelength. We can have different formats by rearranging. So frequency equals velocity over wavelength. Wavelength equals velocity divided by frequency. We can rearrange velocity equals distance over time. So if we want d, it's distance equals velocity times time. Or if we wanted time, right? Time would be equal to distance divided by velocity. Okay, so let's go ahead and take a look here at a few examples that are going to use the formulas that we've just discussed. Okay, so it says a 320 hertz tuning fork will produce a wave of what wavelength in air at 22 degrees Celsius. So a couple things going on there. So first of all, what we need to do is figure out, okay, what the speed of sound is going to be, what the speed of the wave is going to be, and that's going to be determined by using our formula. So the one from above, where it's 331 plus 0.6 times the temperature. Okay, so the first thing we're going to have to do is find the speed of the wave. Okay, and the speed of the wave is then going to be able to, once we plug that in, we'll be able to find the wavelength because we already know the frequency. So again, first step, we're going to find the speed of the wave, so velocity, remember the sound is 331 times 0.6 plus 0.6 times t, so 331 plus 0.6 times t, which is the temperature, which is going to be 22. So what we got there is 331 plus, so 0.6 times 22, that's going to be 13.2, okay, and then, okay, so we add those together, and I'm going to get a speed of 344.2 meters per second. So that's the speed of sound, okay, which is going to be the speed of our sound wave. So step 2, okay, I'm going to plug in to find the wavelength. So remember our rearranged formula: wavelength is velocity over frequency. So wavelength equals velocity divided by frequency, right? We just found our velocity here. This is the velocity of the sound, or the sound wave. So that's going to be 344.2 divided by the frequency, which we're already given here, right? 320 hertz, that was our frequency. So we're going to find that that gives us a wavelength of 1.08 meters. All right, so again, first step, determine the speed of the sound wave. 331 plus 0.6 times the temperature of 22 Celsius. Multiply these two numbers first, 0.6 times 22. Okay, you get 13.2, and you add 331 plus 13.2, 344.2 is the speed of the sound wave. And then we use the rearranged formula, okay, where we have wavelength equals velocity divided by frequency, divide the velocity 344.2 by frequency, which is 320, and we get 1.08 meters for the wavelength. All right, let's take a look at another example here. It says we see a bolt of lightning, and 4 seconds later we hear the thunderclap. You may have experienced this before. You see a flash of lightning, but it's a certain period of time before you hear the clap of thunder. Okay, and again, we talked about sound takes time to reach our ears. Okay, so sound takes a certain amount of time to reach our ears based on, again, certain conditions, like the temperature of the air and so forth. So 4 seconds later, we hear the thunderclap. The speed of sound in air is 0.2 miles per second. So they're giving us a little different units here. How far away is the lightning? So we know velocity or speed equals distance over time. Let's see what we already are given. 4 seconds, what is that? That's time, that's t. Okay. The speed of sound in air, so 0.2 miles per second, that's going to be our v. And it says, how far away is the lightning? Okay, so we know v and we know t. So remember, rearranging this, we want distance. It's velocity, remember, cross multiply here. Velocity times time. So I can say distance equals velocity, which is 0.2 miles per second, times the time, which is 4 seconds. And what we end up with is the distance being 0.8 miles. Okay, so a little different units there. We have units of miles per second rather than meters per second. But again, a bolt of lightning. Okay, we see it. 4 seconds later, we hear the thunder. So 4 seconds is our time. Speed of sound in air is 0.2 miles per second. Again, they converted it to miles per second there. How far is the lightning away? So how far, keywords, tells us we want distance. Okay, we want to solve for the distance. So velocity equals distance over time. Rearrange, distance equals velocity times time. So distance equals 0.2 miles per second times 4 seconds. And we end up with 8 miles. Okay, or 0.8 miles. I'm sorry. All right. This next one says, how many seconds will it take an echo to reach your ears if you yell toward a mountain 82 meters away? So 82 meters is what? That is distance. On a day when the air temperature is 0 degrees Celsius. All right, so this is our temperature, which was capital T. All right, so first thing we need to do is figure out the speed of sound in air. And actually, we already know the speed of sound at 0 degrees Celsius is 331. Let's verify that though. So our V, speed of sound here, 331 plus 0.6 times 0. Right? Because that's our capital T, that's our temperature. 0 times anything just cancels that out. So we know that the speed of sound in this case is 331 meters per second. Now it says how long is it going to take? So how many seconds? We want time here. We got to find the time, which is going to be lowercase t, right? Because in our second step, we're going to use our relationship velocity equals distance divided by time. And we can rearrange that and say that time is equal to distance divided by velocity. Okay? So, with that said, we have our distance, which is 82 meters. We have our velocity, or speed of sound, 331. So we take time equals 82 meters, or 82 divided by 331, okay, and that's going to end up giving me 0.25 seconds. So a quarter of a second it's going to take for the echo to reach my ear. But actually, we have to think of the mountain being 82 meters away. 0.25 seconds, that's only the time for one leg of the trip. So really the total distance traveled, okay, is 82 meters to the mountain and 82 meters back to my ear. So it's going to take 0.25 seconds plus 0.25 seconds, right, for the trip that the sound takes from my mouth to the mountain, and then it's going to take another 0.25 seconds to travel another the 82 meters back. So really, the total time is going to be 0.5 or half a second. All right. So again, 0.25 seconds. That's just basically for half the trip, for the sound to go one way to the mountain. Then it has to and then it's going to take 0.25 seconds for that sound to come back. So our total time that it's going to take is a half a second, or 0.5 seconds. Okay. So these are some examples of calculating quantities related to the speed of sound. Okay, and until next time, this is Mr. P signing off.